Hello, welcome to this video. So in this video we're going to be talking about a beautiful number known as the golden ratio. Now the golden ratio has a rich history. The golden ratio has links to the Fibonacci spiral. So there is such a thing as the golden spiral, and therefore the golden ratio plays an important work in many aesthetically pleasing pieces of art. The golden ratio also plays a role within the Fibonacci sequence itself, and therefore does have some ties to certain things within the natural sciences. Furthermore, the golden ratio leads us to be motivated to construct something called a golden field. So in this video there will be lots of mentions of gold and beauty, but also a pattern and unification. And I think those ideas are the beating heart of mathematics and the mathematical sciences. So let's explore the wonderful world of the golden ratio together and fly to the divine heavens of Platonic mathematics. As highlighted, the golden ratio is kind of geometrically beautiful. So it makes sense that we start hearing a lot about the golden ratio in the civilization of the ancient Greeks. And the ancient Greeks loved geometry, and they were particularly fascinated by structure, and therefore beauty in terms of visual or aesthetic beauty. So naturally the golden ratio would appeal to them. And so the best place to look really, in terms of beginning our journey to learn more about the golden ratio, is none other than the master of geometry himself, the great Euclid. And in Euclid's Elements, Euclid essentially describes what today we would refer to as the golden ratio, where he says the extreme and mean ratio. Now today we say the golden ratio, but you know, that's our kind of poetic license, if you will. Actually the symbol, slightly diverging, but the symbol for the golden ratio, phi, is the way it is because there was a sculptor in ancient Greece who made lots of sculptures using the golden ratio, and his name was Phoebus, and consequently the golden ratio is attributed the term phi, or the symbol phi, after him. So that's why we use phi for that. But anyway, going back to Euclid, Euclid described what today we will call the golden ratio as the extreme and mean ratio. Now this is incredibly vague, but he did thankfully expand on what he meant in his Elements. And so in Euclid's Elements we can read, a straight line is said to be cut into extreme and mean ratio. So it's said to kind of display the geometric ratio by how it's cut, when as the whole is to the greater segment, so the greater is to the less. So that's kind of right down this rather archaic phrasing, at least archaic by modern standards. So we start with a straight line, and I've drawn a rope. I think it's fairly appropriate for our ancient civilization. Not that the Greeks were necessarily, widely known for their, seafaring capabilities, but ropes feel, something appropriate to if we're talking about ancient cultures. And, if we take this rope and think of it as this kind of straight line, we can divide it, and we can always divide it into two segments, A and B. And the golden ratio is a ratio of these two lengths, such that as the whole is to the greater segment, so is the greater to the less. Now the whole is a whole length, which is A plus B. So the whole is to the greater segment means the ratio of A plus B to A. And then the second ratio that is being discussed, the greater to the less, is the ratio between the length of the greater or larger segment and the length of the smaller segment. So the second ratio being discussed is the ratio between A and B. And we can represent ratios as fractions. And so using all of that, Euclid's Elements is telling us that our golden ratio is being depicted when A plus B all over A is equal to A over B. And we define today the ratio A over B, or the fraction of A over B as we would think about it more likely today, as the golden ratio. Now, here we're thinking of fractions and assigning number to fractions. In ancient Greek times, they probably would have thought of it more like a ratio. So thinking how many parts between the different lengths. But today we think about ratios in terms of fractions mainly. And we define the fraction A over B to be our golden ratio phi. But our golden ratio is set because A over B has to equal A plus B over A. That's the kind of restriction we have on A and B. And that's what these two ways of writing phi do. They restrict the ratio of A to B. Now, this ratio, or this relationship between ratios, already gives some indication of why the golden ratio is particularly beautiful or divine. I mean, Leonardo da Vinci described the golden ratio as divine, and I think part of it comes from the fact that there's a kind of fractal or recursive nature to the definition of the golden ratio. That is, to define the golden ratio, we take something that is very big and we divide that by a big subset of it, if you like. And then we say that that is equal to this very big subset divided by this small subset. So we're kind of breaking things down and dividing the bigger thing by the smaller thing. And phi is such that that ratio works both when we go from dividing the length of the whole rope by the bigger segment to dividing the bigger segment by the smaller segment of the rope. And so this kind of recursive nature of phi, I think, is what leads to its kind of beauty. And we can see its beauty most clearly in something known as a Fibonacci spiral. So here we have a Fibonacci spiral. Now, a Fibonacci spiral can be constructed from drawing a spiral between rectangles whose perpendicular lines have lengths dictated by the Fibonacci sequence of numbers. But it turns out if we add more and more rectangles, we approach something called the golden spiral. And additionally, the kind of Fibonacci spiral, very approximately, after every quarter turn of this Fibonacci spiral, the spiral gets a factor of the golden ratio further away from the origin of the coordinate system, so the place where the spiral began. And so the Fibonacci spiral is kind of connected to the golden ratio fairly deeply, and we'll see more of that when we look in detail at the link between the Fibonacci sequence and the golden ratio. But this kind of spiral you see all over in art. So here we've got a painting of a wave, but there's plenty other kind of examples. And after seeing so many examples, it does become slightly mystical, that this golden ratio keeps appearing. And so, I think there was just something very pleasing about it that everybody I say everybody, many people seem to find appealing. I find it appealing. I'm not, blown away necessarily by just the Fibonacci spiral itself, but I do find it nice. There is some calming elegance to it. Now this has been a very geometrical way to think about the golden ratio, and it's good to begin here because the Greeks thought about mathematics geometrically. I think it gives us some intuition. For example, we can ask what value would we assign to the golden ratio? Now it's worth saying we haven't solved this the equation yet. We don't know what the golden ratio is going to be, but we do know it has to be a positive value greater than 1. We know it has to be positive because the lengths A and B are, links and therefore positive. Additionally, phi has to be greater than 1 because we define A to be the larger segment. So by definition A is bigger than B, so A over B is bigger than 1. So using this geometric understanding, we can already say phi is a positive constant that is greater than 1. But let's be a little bit more precise. What exactly is phi? And that's what we're going to look at in the next part of this video. So now we've got kind of a geometrical intuition for phi, which is a brilliant place to begin. I mean, for the ancient Greeks, so that's like the perfect place to begin. Let's go on to actually get a numerical value for it, actually a perfectly exact one. So we start with our definition for the golden ratio phi. Now importantly with phi there are two ways of writing phi, and the fact that they're equivalent is the cornerstone of the idea of phi. It's the idea that these two ratios are equal, they're the same. And that means that the statement phi minus phi equals 0 isn't trivial. It would usually be trivial, but because we have two ways of writing phi, it isn't a trivial statement. So we can say that A plus B over A minus A over B is equal to 0, because phi minus phi equals 0. And because there we wrote phi in two different ways, after a bit of rearranging, a bit of playing with that equation, we get an equation which just has phi terms and a single number, which is a really good step in working out the value of phi. So here is the equation we get. Now here we've got a phi to the minus 1 term, a phi term and 1, so this is a step towards being able to get a numerical value for phi. However, this is not a polynomial equation because of the phi to the minus 1 term. And physicists really try at all costs to turn things that aren't polynomials into polynomials. Because once we do that, we have so many methods for handling them. So how can we turn this expression into a polynomial? Well, we want to get rid of that phi to the minus 1 term, and we can do that by multiplying everything in the second equation by phi. And that gives us this expression. Now, I personally don't like having negative coefficients next to my highest order term, so I'm going to multiply everything by minus 1, which is just a aesthetic criteria. It's not something you have to do, but well, this is a video about a aesthetically pleasing number, so if there was ever a time to be aesthetically biased, this video would be it. And so we end up with this equation for phi, the golden ratio. And this is a quadratic, and like most quadratics, we actually have two solutions to this equation. And the question is, which one of those solutions is true? So is the golden ratio 1 plus the square root of 5 over 2, or is it 1 minus the square root of 5 over 2? And to answer that, we think back to the geometrical picture of the golden ratio we had. And that picture told us that the golden ratio is the ratio of lengths, and lengths are by their very nature positive, or at least they're non-negative, and therefore the golden ratio has to be non-negative. And so the golden ratio has to be the non-negative root of phi squared minus phi minus 1 equals 0. In other words, our golden ratio is 1 plus the square root of 5 over 2. But what about the other solution to our quadratic equation? How should we interpret that? Well, there are various ways to work it out. I'm going to do a slightly complicated way to work it out, but I think it's very pleasing because it involves seeing symmetries in equations, which I think is kind of cool. So firstly for this, let's note that if we have a value phi which is a solution to 1 plus phi to the minus 1 minus phi equals 0, then it is automatically going to be a solution to phi squared minus phi minus 1 equals 0. So let's look at the second equation in the blue box, the non-polynomial equation, and see if we can use this to work out what the negative root to our quadratic equation would be. Well, clearly the golden ratio is a solution to our non-polynomial equation, but also note that if we replace phi with minus phi to the minus 1 in our second equation in the blue box, we still get back that second equation. So the equation 1 plus phi to the minus 1 minus phi equals 0 has a kind of symmetry in that if phi is a kind of like solution, then minus phi to the minus 1 will also be a solution. So we saw that a solution to this non-polynomial equation was the golden ratio, and so clearly this other expression minus phi to the minus 1 must be the other solution to our non-polynomial equation and therefore to our quadratic. And so we can conclude that minus phi to the minus 1 is the 1 minus the square root of 5 over 2, which itself implies that phi to the minus 1 is equal to the square root of 5 minus 1 over 2. And that's also a cool way to work out the inverse of phi, and we work that out through thinking of the symmetry of a non-polynomial equation, which I just think is kind of cool. But, you know, maybe I've just done a bit too much mathematics, but I think it's quite beautiful. But now we've got kind of like a value for the golden ratio, we can start to talk about some of its properties. So one thing to note is that both the golden ratio and its inverse are irrational numbers. Because the square root of 5 is irrational, and you can prove that through proof by contradiction in the same way that you prove the square root of 2 is irrational, or the square root of 7 is an irrational number. So phi is irrational and in that way is similar to e and pi and other very important numbers in mathematics. But unlike e and pi, phi is an algebraic number. It's a solution to a polynomial with integer coefficients. So the golden ratio is a irrational algebraic number. And it has many other qualities besides. But phi pops up in some unexpected places, and we hinted at one place it might appear when we looked at the golden spiral. We said it was connected to the Fibonacci sequence. So now let's really talk in brief detail really about that connection. So now we understand about how to get a numerical value for the golden ratio phi. Before looking at something called the golden field, which uses the square root of 5 and therefore has some interesting features in terms of irrational numbers being present in the golden field. I wanted to talk about a sequence which I've made previous videos on, called the Fibonacci sequence. Now I think the Fibonacci sequence came up in one video I did involving some coding. And I'll put a link to that in the description. But the Fibonacci sequence is one of those sequences that you probably, if you're really into maths, heard of before, even if you haven't used it. It's one of those iterative sequences which appears in mathematics. And was known long before Fibonacci, but he popularised the sequence, so we call it the Fibonacci sequence. Now the Fibonacci sequence consists of the following terms. The first term is 0, the second term is 1, and to get all other terms we add the two previous terms. Now, because we're using kind of index notation, the first element is denoted as the 0th element. So when I say the first element, I mean U0. When I say the second element or the second term, I mean U1. Slightly confusing, but one does get used to it over time. And it kind of turns out that the ratio of terms, the ratio of consecutive terms of the Fibonacci sequence approaches, in the limit as n goes to infinity, the ratio approaches something involving the golden ratio. I think it approaches the golden ratio itself, or at least it approaches a function simply written in terms of the golden ratio. And here is just kind of a list of, some other elements for n. And I think one nice thing about the Fibonacci sequence is it's kind of filled with pattern. So for example, U3, we take the first, we look at the previous two terms, so from U2, the coefficients of these terms are 1, so we don't write them. We add 1 and 1 and we get 2. So the third term is 2u1 plus u0. For the fourth term, if we look at the coefficients in u3, we have 2 plus 1, which would be 3. And indeed, the fourth term has 3 times u1 in it. So there's lots of patterns. But as well as the limit of the ratio of terms in the Fibonacci sequence being strongly related to the golden ratio, it turns out that you can write this iterative sequence enclosed form, so essentially as a function, and that function, you know, maybe no surprises by now, but that function involves the golden ratio. Phi, but it also involves the other root of the quadratic that yielded the numerical value for the golden ratio, and that other root here is represented by psi. Remember, we found the relationship between psi and the golden ratio phi before. So you might sometimes see Banach's formula written slightly differently using rules of powers. It can be written entirely in terms of the golden ratio. But I like it in this form because it has the golden ratio in it, but also the other root of our quadratic equation that yielded the golden ratio. So I think this is a really cool thing. Now, I'm not spending long on this part of the video because there's another video on this channel that talks more about the Fibonacci sequence. But I think it's a really, really beautiful sequence and well worth mentioning with its connection to the golden ratio in this video. But now we're going to move on to look at the golden field. Now, if you haven't seen fields before in mathematics, I wouldn't worry, I'm going to cover what they are. If you haven't seen a physical field, don't worry, you don't need to know what a physical field is for the next bit of this video. But if you would like to learn more about some of the ideas I'll be talking about in the coming part of the video, where I'll be mentioning fields and binary operations, I'll also put in the description a link to my video about kind of groups, binary operations and all those kinds of things. But anyway, let's now move on to think about how we can think of a number system that incorporates the golden ratio as a kind of special irrational number. And then we'll just kind of wrap everything together. So we've come quite far on our journey, and my camera is also having a bit of a track, it seems. But for this part of the video, the kind of, you know, last part of our tour of the wonders of the golden ratio, I wanted to talk about the golden field. Now, when making the video, I thought quite carefully about what image can I use to represent something as abstract as the field, and ideally even the golden field itself. How can I represent this visually in a familiar way? However, I came across a meme, and the meme had "What is a field?" as the title. For kind of the agriculture setting, it had a traditional type of field filled with wheat and other things. For the physics people, it had a picture of an electromagnetic wave, so an electromagnetic field. And then for mathematicians, it just had a completely black box with the formal definition of a field in it. And I think that speaks volumes of how abstract fields are. Now, that meme couldn't find any way to visualize a mathematical field. Or at least, you know, kind of humorously, I mean very humorously commenting on how hard it is to find a good visual example of a field, if by a field we mean what a mathematician would mean. So, you know, I just kind of gave up, and instead we've got an image of a literal golden field, a field filled with golden wheat. Sadly, I can't, you know, offer you rules on how to construct a field that is composed of golden wheat, but I can show you how to construct the golden field. So let's have a go here. So for the golden field, we have to start with breaking down the term to understand how to make it. Well, the golden part of it is to do with the inclusion of the golden ratio. The field part of it is something that needs a bit more explanation, I think. So a field is a set of numbers in which we can map numbers to each other and keep these numbers within the set using the operations that are between them, such as addition and multiplication. Now the key thing with this set of numbers and the operations addition and multiplication is these operations aren't allowed to combine elements to create an element that is outside of that original set. And another thing to note with a field is I'm using terms like addition and multiplication. I really mean addition like and multiplication like operators. So operators which fulfill a similar kind of role. They don't have to literally be addition and multiplication. And by multiplication like, for example, I mean we can define a multiplicative inverse of each element in the field apart from the neutral element of the addition operation. So, there's a lot of kind of technical jargon there, but there are essentially constraints, general constraints, that mean that our multiplication-like operator has to be multiplication-like if it's going to be part of this field. So a field is a set of numbers where we have addition-like and multiplication-like operators, and these operators can combine elements of the set that's helping form this field to produce another element, but that other element is already contained within our field. So we have this kind of closed system of numbers. Or at least usually it's numbers. It doesn't have to be, but for our purposes it will be. Now we can think about what kind of fields are we familiar with. Well, one type of field we're definitely familiar with is the real number line combined, well I should say the set of real numbers, combined with the traditional operations of addition and multiplication. You've been using them since time immemorial. It's a very familiar field to us. A slightly more particular field is the set of irrational numbers combined with the operators of familiar addition and multiplication. Now this is still a field because if we add two rational numbers we get another rational number, and if we multiply two rational numbers we get another rational number. And you kind of presume that when you're adding and multiplying fractions in one's earliest days of mathematics. So, this is a property one uses. One uses the idea that the set of rational numbers help form a field, although one doesn't usually think of it like that, but one uses this idea throughout one's entire life. So, a useful field might be a set of rational numbers combined with common operations of multiplication and addition. And by common I mean multiplication and addition as we're familiar with them. Now a natural question comes about when we ask, well, how can we bring the golden ratio phi into this field? Because it's worth saying it's not at the moment part of the field. The field is too constrained because the field only has rational numbers. It doesn't have irrational numbers. And because the operators in the field aren't allowed to produce an element outside that field, it means that essentially this field is just stuck with rational numbers. So how can we bring irrational numbers to forge the golden ratio within a kind of extended field, building from this field involving our set of rational numbers? Well, what's the smallest number of things we need to add to this set of rational numbers, such that this new set, this enlarged set, will contain the golden ratio? Well, we saw that the golden ratio contains the irrational number, the square root of 5, and that's the only irrational number it contains. So if we imagine the set Q, so the set of irrational numbers, and then we also add to that set the square root of 5, suddenly we can define a field involving the set of Q and with also the square root of 5 in which the golden ratio exists. And also, thanks to addition being an operation within this field, the inverse of the golden ratio will also exist. And therefore both phi and psi exist within this kind of extended field. And we call this extended field, where we've added the square root of 5 to the set of rational numbers, we call this extended field the golden field. It's, if you like, the minimal field that contains the golden ratio. And minimal in that we're adding the minimal amount we need to the set of rational numbers to allow us to create a field that contains the golden ratio. We could, for example, have also added the square root of 2. We don't need to do that to get the golden ratio, but that would be a way of extending our field even further. Now, the golden field has a very interesting kind of philosophy behind it, because in the golden field, the square root of 5 is an incredibly unique and alien kind of number. We've kind of pulled square root of 5 into it, but the square root of 5 is completely unlike the other numbers that surround, because the other numbers are rational numbers. So the square root of 5 has been added to a group of numbers that are nothing like the square root of 5 to allow us to build a new magical number called the golden ratio. Now, the idea of adding a number that is totally unlike the other numbers to develop new numbers might sound familiar. That's exactly what we do when we're creating the complex plane and building complex numbers. We take a number that is unlike any real number, like the square root of -1, and then we use addition and multiplication to combine it with real numbers, and suddenly we end up with complex numbers. And so there's an analogy that we can make between complex numbers and numbers containing the square root of 5 in the setting of the golden field. So in the golden field, the square root of 5 is analogous to the unit imaginary number in the complex plane. And this encourages, this motivates us to think about the golden field as having a structure very similar to that of the complex plane, and in fact papers have been written on that very topic. And just to give a brief taster, we can define in the golden field something called the algebraic conjugate. And algebraic conjugation works very analogously to complex conjugation, with now the square root of 5 taking the role of the unit imaginary number. And so if we have a element alpha within our golden field, and alpha is a plus b times the square root of 5, where a and b are rational numbers, then alpha bar, that is the algebraic conjugate of alpha, is defined to be a minus b times the square root of 5. And the algebraic conjugate actually has very similar algebraic properties to the complex conjugate. And one could, go off on a whole tangent exploring that. And I think just for exploring different number systems, different ways of thinking about numbers, it's worth mentioning the golden field. But another reason why it's worth mentioning is because the golden field is an example of where we've taken a set of rational numbers and we've extended it by adding an irrational number. And this idea of extending fields by adding numbers that lie outside the type of numbers in the starting field, that idea is used all the time in Galois theory. And Galois theory tells us about what kind of polynomials we can have solutions for. And when I say a solution, I mean a generic equation that is in closed form and allows us to solve a general polynomial of that degree. So, for example, Galois theory tells us that yes, we should have quadratic equations. We should also have a formula for solving cubic equations. That formula was found by a group of Italian mathematicians in the 16th century. It took us some time to get there, but we eventually got there. But Galois theory also tells us we should not expect, in fact we cannot find, a closed form formula for solving fifth order, so quintic polynomial equations. So Galois theory takes the idea of extending fields and does some really cool things with them. And, a beautiful example of an extended field is the golden field. So that's kind of, a good place to leave kind of this topic, for now at least, where we have raised ourselves to the golden streets of a mathematical heaven, and seen and studied things that are beyond accurate visual depictions, and so hopefully you can forgive me for having a mildly random picture of a bunch of golden wheat on the screen. But I wish you an amazing day ahead, and I look forward to sharing some more wonderful physics and mathematics with you soon. And for those following the channel, stuff on general relativity and research is going on in the background, but I have got in the meantime another video on a very special number, Euclid's number, which is very important for solving linear differential equations and therefore has tons of applications in physics. I've got a video coming up on that very special number soon. But for now, I wish you all the best. Have a great week, and always stay curious.